Imagine this. Everything you see, galaxies, gravity, atoms, time itself looks random. Stars explode without warning. Planets form by accident. Life appears like a coincidence. But what if that's an illusion? What if the universe is not random at all, but strictly constrained by invisible rules we still don't fully understand? And what if the most shocking part is this? The deeper you go into chaos, the more order you actually find. Because at every scale, from quantum particles to galaxies, something strange is happening. Nothing is truly free. Nothing is truly random. Everything is following a hidden structure, and once you see it, you can't unsee it. The illusion of randomness. When we look at the universe from a distance, everything seems unpredictable. A star explodes in a distant galaxy without warning. A planet forms in a swirling cloud of gas. A storm appears, grows, disappears. Even life itself begins in ways that look accidental, almost like nature is experimenting without a plan. And from our point of view, this creates a powerful assumption that reality is random. But randomness is often not what it appears to be. What we call random is simply a system so complex that we cannot trace every cause behind it. It is not the absence of order. It is order operating at a level too detailed for the human mind to track. When too many variables interact at once, the outcome becomes unpredictable, even if every step in the process is fully governed by rules. Think about a simple example. Smoke rising from a flame. At first glance, it looks chaotic. The movement twists, breaks, and spreads in unpredictable directions. But beneath that apparent disorder, every particle of smoke is following strict physical laws. Gravity, pressure differences, fluid dynamics, molecular collisions. Nothing in that system is actually free. It only appears free because the number of interacting parts is enormous. The same pattern repeats across nature. Weather systems behave wildly, yet they are driven by temperature gradients, pressure systems, rotation of the planet, and energy exchange in the atmosphere. Ocean currents shift and spiral, but they are tied to gravity, salinity, temperature, and Earth's rotation. Even in finance, human behavior looks unpredictable at the individual level, but at a large scale, it begins to follow statistical patterns shaped by collective behavior and constraints. What changes is not the presence of order, but our ability to see it. As we move deeper into science, this illusion becomes even more interesting. In classical physics, systems like planetary motion were once thought to be complex and unpredictable over long timescales. But with better mathematics, we discovered that those same motions follow precise equations that can predict positions far into the future and past. What once looked like uncertainty was revealed to be structure expressed through mathematics. This leads to an uncomfortable idea. Randomness may not exist in the way we imagine it. It may be a label we use when we reach the edge of our understanding. This becomes even more subtle. Particle behavior appears probabilistic. We can calculate chances, distributions, likelihoods, but not exact outcomes. A particle does not land in a single predictable position. It exists in a range of possibilities until measured. To many, this looks like pure randomness at the foundation of reality. But even here, the randomness is not uncontrolled. It is bounded by strict mathematical frameworks. Probabilities are not chaos. They are structured constraints. The universe does not allow anything to happen. It only allows specific ranges of outcomes defined by deep equations. So the question shifts. If everything we call random is still constrained by rules, then is it truly random at all? Or is it simply order expressed in a form too complex, too layered, or too fundamental for direct observation? The illusion of randomness begins to form when we stand too far away from the underlying structure, or when the structure itself is operating at a scale beyond direct human intuition. From that distance, patterns dissolve into noise, and noise feels like absence of design. But absence of visible structure is not the same as absence of structure itself, and this is where the deeper tension begins. Because the more we study reality, the more it seems that randomness is not something the universe contains, but something the universe only appears to have when viewed from the wrong level of scale. Order hidden inside chaos feels like the absence of structure. It looks like things falling apart without direction. Systems breaking, patterns dissolving, outcomes becoming impossible to predict. But when we study chaos more carefully, something unexpected appears. Chaos does not destroy order, it hides it. The universe rarely behaves like a clean diagram. Instead, it behaves like a crowded system where too many interactions happen at once for the human mind to follow individually. When that happens, we stop seeing clear cause and effect, and we start seizing motion that feels irregular. But irregular does not mean ungoverned. Take something as simple as boiling water. Inside a pot, thousands of invisible movements are happening at the same time. Molecules are colliding, separating, exchanging energy, forming temporary clusters, and breaking apart again. From the surface, we see bubbles rising and collapsing in unpredictable ways. It looks random because no single human observer can track each microscopic interaction. Yet every movement is still governed by temperature, pressure, and molecular physics. There is no moment in that boiling water where a particle chooses to break a rule. It only follows rules so many times, in so many directions, that the final pattern becomes unreadable as a single sequence. Chaos, in this sense, is not the opposite of order. It is ordered multiplied beyond direct recognition. Now consider something much larger: weather systems. A storm seems unpredictable because small changes in air pressure or temperature can dramatically shift its outcome. A tiny variation in one region can change the path of wind hundreds of kilometers away. This sensitivity creates what we call chaotic behavior. But again, every component is still obeying strict physical laws. Air does not randomly decide to move upward or downward. Water vapor does not ignore thermodynamics. The atmosphere is not improvising. It is executing a vast network of interacting rules where small causes amplify into large effects. What creates the illusion of randomness is not the absence of law, but the extreme sensitivity of the system to initial conditions. When a system is sensitive enough, even perfect knowledge becomes insufficient for long-term prediction. That does not mean the system is unstructured. It means the structure is too finely detailed for complete forecasting. This pattern repeats across nature in surprising ways. In orbital systems, 3 or more interacting bodies can create motion that looks unstable and irregular. The famous three-body problem shows that even classical gravity, one of the most well-understood forces, can produce behavior that appears chaotic over time. Yet even in that complexity, nothing is breaking physical law. The system is not escaping structure. It is exploring every possible configuration allowed by that structure. Chaos also appears in something as ordinary as a river. Water flowing downstream bends, splits, collides, reforms into streams and vortices. From above, it looks like disorder, but every twist in the flow is shaped by gravity, terrain, friction, and fluid dynamics. If you could zoom into every particle and calculate every force, the river would stop looking random. It would become a fully determined evolution of energy moving through space under constraint. This is where an important shift in perspective happens. Chaos is not what happens when laws fail. It is what happens when laws interact at scale. When a single rule operates alone, the result looks simple. When thousands or millions of rules interact simultaneously, the result becomes layered, nonlinear, and difficult to track. But difficulty in tracking is not the same as absence of order. Modern science often finds that chaotic systems carry hidden structure inside them. Patterns emerge in turbulence. Statistical regularities appear in seemingly disordered systems. Even in randomness-like environments, distributions settle into predictable forms when observed long enough or across large enough samples. This suggests something deeper. Chaos may not be a breakdown of order, but a transformation of order into a different expression. One that is distributed, compressed, and encoded rather than obvious. Chaos is not the enemy of understanding. It is simply the point where understanding must change its form. Instead of tracking individual events, we begin tracking probabilities. Instead of predicting exact outcomes, we describe boundaries. Instead of looking for straight lines, we look for constraints that shape motion from behind the scenes. And when we begin to see chaos this way, something subtle changes in how reality feels. The universe stops appearing like a collection of unpredictable events and starts appearing like a system operating under layers of invisible structure. Structure that does not disappear when things become messy, but becomes harder to recognize because it is expressed through complexity rather than simplicity, the law that never breaks. If there is one idea that quietly holds modern science together, it is this: something in the universe never breaks its rules, no matter how extreme the situation becomes. From collapsing stars to subatomic collisions, certain quantities always remain accounted for. They do not vanish, they do not appear from nothing, and they do not escape the system. They simply move, change form, and continue. This might sound like a simple bookkeeping trick, but the deeper you go into physics, the more this bookkeeping becomes the backbone of reality itself. Take energy, for example. In everyday life, energy seems to disappear. A moving ball stops. A hot object cools down. A swinging pendulum slows until it rests. From a casual viewpoint, it looks like energy is being lost. But when we examine the system carefully, something else is happening. The energy is not gone. It is transferred into heat, sound, microscopic motion, or radiation. It spreads out, becomes less visible, harder to extract, but it does not break its total count. This idea is not limited to mechanical systems. It extends across every physical interaction we know. In particle physics, when particles collide at high energies, they can transform into entirely different particles. What was once mass can become radiation. What was once a single particle can become many. Yet even in these extreme transformations, the total energy before and after remains consistent within exact mathematical limits. This consistency is not an assumption added to physics. It is something that emerges from deeper structure. In modern theory, conservation laws are not arbitrary rules imposed on nature. They are consequences of symmetry. If the laws of physics behave the same today as they did yesterday, then energy is conserved. If space behaves the same everywhere, momentum is conserved. And if physics does not favor any direction in space, angular momentum is conserved. This means something important. Conservation is not enforced. It is inevitable. The universe does not try to preserve these quantities. It cannot avoid preserving them, as long as its underlying structure remains unchanged. In that sense, conservation laws are not restrictions placed on nature. They are descriptions of what nature is allowed to be, if it is consistent with itself. This is why these laws feel so universal. They do not depend on location, scale, or material. The same principles that govern a falling stone also govern a galaxy rotating over billions of years. The same rules that apply inside a particle accelerator also apply inside a collapsing star. The system changes, but the accounting never fails. But what makes this even more striking is how invisible the enforcement is. There is no central mechanism checking each interaction. There is no physical entity monitoring every transformation and correcting errors. Instead, the structure of reality itself ensures that violations cannot occur. It is as if the universe is built in such a way that breaking the rule is not just forbidden, it is impossible. This raises a deeper question. Why does this structure exist in the first place? We can describe how conservation works with extreme precision. We can calculate it, test it, and confirm it across vast ranges of energy and scale. But the reason why the universe is constructed in a way that allows such perfect conservation is not something physics currently explains. We observe the consistency, but the origin of the consistency remains outside the equations. This is where the idea becomes more than just physics. It becomes a statement about the nature of reality itself. Because if something is always preserved, no matter how violent or complex the process, then that something is not just a feature of events, it is a feature of existence. Every explosion, every collapse, every transformation in the universe is constrained by it. A supernova cannot produce energy beyond what existed in its system. A black hole can't not erase the total accounting of mass energy. It only hides it behind horizons. Even the vacuum of space, which seems empty, is governed by energy structures that fluctuate but remain bound within strict limits. The law does not weaken at extreme scales. It does not fade in chaotic conditions. It does not fail at the edge of the universe. It remains stable whether the system is simple or unimaginably complex. And because of that, it becomes easy to overlook. We notice dramatic changes, stars dying, galaxies colliding, particles transforming, but we rarely notice the invisible constant that ensures nothing is lost in the process. This is the strange nature of a law that never breaks. It is most powerful when it is least visible. It does not announce itself. It does not interfere. It does not need to. Every event in the universe already obeys it automatically, as if reality has no alternative but to remain internally consistent. And once you recognize that pattern, a subtle realization begins to form. The universe may appear dynamic, unstable, and constantly changing on the surface, but underneath every change, there is something that never moves out of place. Why physics looks predictable. The universe feels like it follows a quiet sense of order. Objects fall in consistent ways. Planets move along stable paths. Light travels at a constant speed, and even distant galaxies behave according to patterns we can calculate. This creates a powerful impression that physics is predictable because reality itself is simple and stable. But that impression hides something deeper. Physics looks predictable, not because the universe is simple, but because the universe is constrained in ways that remove almost all possible alternatives. When we say something is predictable in science, we do not mean we can foresee every detail of its future with perfect clarity. We mean that, given a set of conditions, only certain outcomes are allowed. The system may be complex, even wildly complex, but it is not free to behave in any arbitrary way. Its behavior is filtered through mathematical rules that eliminate impossible paths before they ever appear. Take planetary motion. For centuries, the movement of planets was thought to be mysterious and perhaps even irregular. Early models struggled to explain small deviations in orbits. But once gravity was properly understood, those same movements became predictable to extraordinary precision. Planets do not drift randomly through space. They follow curves defined by mass, distance, and gravitational interaction. Even when multiple bodies interact, creating complex gravitational effects, the system still remains governed by equations that do not change. What changed was not the behavior of planets, but our understanding of the structure behind that behavior. This pattern repeats across all of physics. When we observe a system closely enough and identify the underlying constraints, predictability emerges, not because the system becomes less complex, but because the space of possible outcomes shrinks. Imagine a river flowing through a valley. From a distance, the water may look chaotic as it bends, splits, and rejoins. But the river is not choosing its path. The shape of the land, the pull of gravity, the friction of terrain, and the properties of water itself are continuously narrowing the directions it can take. The river appears to decide its motion, but in reality, it is being guided by boundaries it cannot escape. Physics works in a similar way. Every physical system exists inside a set of constraints. These constraints are not visible objects, but mathematical relationships that define what is possible. They act like invisible walls around reality, limiting the directions in which change can occur. This is why even systems that appear chaotic at first often reveal deep predictability when studied carefully. Weather systems, for example, are famously difficult to predict in detail. A small change in air conditions can lead to dramatically different outcomes. But even in that sensitivity, the system is not random. It is bounded by thermodynamics, fluid dynamics, planetary rotation, and energy transfer laws. These constraints do not allow the atmosphere to behave in just any way it wants. They only allow a narrow range of physically valid behaviors. So predictability in physics is not about simplicity. It is about restriction. The universe does not need to simplify its behavior for us to understand it. Instead, it already exists in a form where many possibilities are never available in the first place. This becomes even clearer in the microscopic world. At the level of particles, behavior is often described using probability. This is where many people assume predictability breaks down completely. If we cannot know exactly where a particle will be, it sounds like physics has lost its ability to predict anything at all. But that is not what is happening. What we call uncertainty in quantum physics is not the absence of rules. It is the presence of rules that define probability itself. Particles do not behave randomly in an unrestricted sense. They follow probability distributions that are precisely calculated and experimentally verified. These distributions are not guesses. They are mathematical structures that constrain outcomes just as firmly as classical laws constrain planetary motion. In other words, even uncertainty is structured. It does not mean anything can happen. It means only certain ranges of outcomes can happen, with precise likelihoods assigned to each. This is a very different kind of predictability. It is not the predictability of a single outcome, but the predictability of a boundary within which all outcomes must fall. Another reason physics appears predictable is that many systems in nature tend to evolve toward stable configurations. Unstable states often collapse, disperse, or transform into more stable arrangements. This creates a natural filtering effect. Over time, systems that survive are often those that fit within stable patterns, while unstable configurations vanish or transition quickly into something more organized. This stability bias makes the universe look even more orderly than it might initially seem. We are more likely to observe systems that persist long enough to be measured, and persistence itself often requires structural stability. There is also a deeper mathematical reason behind predictability: symmetry. When the laws of physics remain unchanged under transformations, such as shifting in time, moving in space, or rotating in direction, those symmetries impose strict constraints on how systems behave. These constraints are not optional. They are built into the fabric of the equations themselves. They force conservation, limit variation, and ensure consistency across scales. Because of this, physics is not just a collection of observations about how things behave. It is a system built on invariance, on the idea that certain properties must remain unchanged, no matter how you look at them. This invariance is what makes prediction possible at all. If the rules themselves could change from moment to moment, or place to place, no amount of observation would allow us to generalize. But because the rules remain stable, patterns can be extended beyond the moment they are observed. And that stability is why physics feels predictable, even when the systems it describes are incredibly complex. So what we experience as predictability is not the simplicity of nature, but the consistency of its limitations. The universe is not predictable because it is easy. It is predictable because it is not free. Every event unfolds inside boundaries that were already fixed before the event began. And once you recognize that, predictability stops being a sign of simplicity and becomes evidence of structure so strict that even chaos cannot escape it. Symmetry, the invisible rule. If there is a single idea that quietly sits underneath almost every law in physics, it is symmetry. Not symmetry in the sense of shapes or beauty, but something far more abstract. The idea that the rules of the universe do not change when you change your perspective. This sounds almost trivial. Of course, physics should behave the same way tomorrow as it does today. Of course, gravity should work the same here as it does 1 billion kilometers away. But when you look deeper, this, of course, turns into something far more powerful. Because without this consistency, nothing in the universe could be understood at all. Symmetry means that certain transformations do not alter the outcome of physical laws. You can shift an experiment in space, rotate it in any direction, or repeat it at a different time, and the underlying rules remain unchanged. The equations do not adjust themselves based on where you are or how you are looking at them. They stay fixed. This stability is not just a convenience for scientists. It is the reason science works in the first place. If the laws of physics changed depending on location, then every experiment would give a different answer depending on where it was performed. If the laws changed over time, then past observations would not help predict future behavior. If direction mattered fundamentally, then turning a device slightly would change its outcome in unpredictable ways. In such a universe, there would be no consistent pattern to discover, only isolated events with no transferable meaning. But that is not the universe we live in. Instead, the universe behaves as if it is indifferent to perspective. It does not care where you are, when you are, or how you orient yourself in space. The rules remain the same, and that indifference is what makes structure possible. This is what symmetry really is: a hidden uniformity in the rules themselves. And from this uniformity, something remarkable emerges. When a system has symmetry, it automatically produces conservation laws. This is not an added feature, it is a direct consequence. If the laws of physics do not change over time, then energy must be conserved. If they do not change across space, then momentum must be conserved. If they do not change when rotated, then angular momentum must be conserved. This connection reveals something deeper. Conservation is not an independent principle. It is the shadow of symmetry. In other words, what we observe as things staying the same is not enforced by a physical mechanism holding them in place. It is a reflection of the fact that the universe's underlying rules do not shift depending on how you move through it. This is where symmetry becomes more than just a mathematical idea. It becomes a structural principle of reality. To understand it more intuitively, imagine a world where symmetry does not exist. In such a world, physics in one region might behave differently than in another. A force that pulls objects downward in one place might push them sideways in another. Time might flow at different rates, depending on location, without any consistent pattern. In such a universe, no general laws could be written, because every law would have exceptions built into the fabric of space itself. There would be no universal explanation for anything. Every phenomenon would be local, isolated, and unrepeatable in a meaningful way. Learning would not accumulate, because knowledge from one situation would not apply to another. That kind of universe would not just be confusing. It would be fundamentally unbuildable. No stable structures, no persistent systems, no reliable evolution of complexity. Symmetry prevents that collapse of structure. It ensures that the same rules apply everywhere, allowing patterns to extend across distance and time. It is the reason we can study distant galaxies and trust that gravity behaves there the same way it behaves here. It is why physics discovered on Earth can describe events billions of light years away. But symmetry does something even more subtle. It restricts what kinds of changes are allowed, because if the laws remain unchanged under certain transformations, then not all possible motions or interactions are permitted. The system is constrained to evolve in ways that respect those invariances. This is why symmetry is not just a passive property. It actively shapes the behavior of everything in the universe. Symmetry is not something that sits inside the universe as an object. It is a statement about the universe's structure itself. It tells us that the rules are written in a form that does not depend on perspective. And this is where the idea becomes almost unsettling. We do not observe symmetry directly. We infer it from consistency. We see that experiments agree across time, space, and orientation, and from that agreement we conclude that symmetry must exist. But symmetry is not something we see in the same way we see objects. It is something we detect through the absence of variation, where variation could have existed. This makes it one of the most invisible but powerful ideas in all of physics. It is not a force. It is not a substance. It is not a field. Yet it determines what forces can exist, what quantities must be conserved, and what transformations are allowed in the first place. In that sense, symmetry is not just part of the rules of the universe. It is the reason the universe has rules at all that can remain consistent across everything we observe. When symmetry becomes reality, symmetry is usually described as something you observe from the outside. A snowflake looks symmetrical. A circle looks symmetrical. A building, a face, a pattern in nature, all of these are judged by how balanced they appear. But in physics, symmetry is not just a visual feature. It is not something added to reality after the fact. It is something reality obeys before anything even exists. To understand this properly, you have to drop the idea that symmetry is about appearance. In physics, symmetry means something deeper. It means the rules do not change when you change perspective. If you rotate a system, shift it in space, or move it forward in time, the underlying laws stay identical. Nothing inside the equations cares about direction, position, or orientation. The universe does not notice your change of viewpoint. That sounds simple at first, but it leads to something far more extreme. If the rules never change under rotation, then nature has no preferred direction. If the rules never change under time shifts, then nature has no preferred moment. And if the rules never change under movement through space, then nature has no preferred location. This removes anything that could act like a special frame for reality. No center of importance, no privileged axis, no hidden direction where things behave differently. Now here is where symmetry stops being abstract and starts becoming physical reality itself. Because once a rule is truly symmetric, it forces the system to behave in a very specific way. It does not allow random outcomes without structure. It does not allow violations without consequence. It constrains how everything evolves. In other words, symmetry is not passive. It actively shapes what is possible. For example, if you take a system and rotate it slightly, and the laws remain unchanged, then any physical quantity that depends on rotation must follow strict conservation rules. This is not an assumption. It is a mathematical requirement. The structure of the laws forces a corresponding structure in the behavior of matter. What looks like freedom in motion is actually limited by invisible constraints. This is the point where symmetry stops being something in the background and starts acting like something embedded inside reality. It is no longer describing the universe. It is defining what the universe is allowed to do. At microscopic scales, this becomes even more striking. Particles do not choose directions randomly in the way we imagine randomness in everyday life. Their behavior is tied to symmetrical laws that treat all directions equally. Even when outcomes look uncertain, the probabilities themselves are shaped by symmetry. Randomness is not free-floating chaos. It is structured uncertainty inside strict boundaries. At larger scales, the same principle repeats. When gas clouds collapse into stars, when stars organize into galaxies, when galaxies arrange into clusters, the resulting structures do not break symmetry at the level of underlying laws. They may appear uneven, but the rules guiding them remain perfectly balanced. The asymmetry you see is not from the laws. It is from how systems settle into configurations that are allowed under those laws. This leads to a strange realization. Symmetry does not prevent structure. It produces structure. Without symmetry, physics would not be stable enough to form anything recognizable. There would be no consistent forces, no predictable interactions, no repeatable outcomes. Reality would not hold together long enough for complexity to exist. So, symmetry is not just a property of equations written on paper. It is the reason those equations correspond to anything real. It is what allows matter to behave consistently across time and space. It is what keeps the universe from becoming arbitrary. But there is a deeper layer still. When symmetry is perfect, it does something unexpected. It becomes invisible. You cannot detect it directly because every direction looks the same. Every moment behaves the same. Every position follows the same rule. Symmetry disappears into the background of experience, not because it is absent, but because it is everywhere at once. And that is the point where symmetry stops being a concept and becomes reality itself. Not something the universe has, but something the universe is built from. The universe does not decide, it constrains. When people think about how the universe behaves, they often imagine something like choice, as if nature is constantly deciding what to do next, where a particle should go, how a system should evolve, what outcome should appear. That idea feels natural because human thinking is built around decisions and intentions. We assume something must be selecting outcomes from a range of possibilities. But physics does not work like that. At no level of reality is there evidence that the universe is making decisions. What exists instead is something more rigid and far less flexible. Constraint, not choices, not preferences, boundaries that cannot be crossed. A constraint is not an action. It is a limit on action. It does not guide reality toward a goal. It eliminates anything that violates structure. And once you start looking at physics through this lens, the entire picture of reality shifts from something active to something restricted. Take motion, for example. A planet orbiting a star does not choose its path each moment. It follows a trajectory determined by gravitational constraints and conserved quantities like energy and angular momentum. At every point in its motion, there are only a limited number of possible directions it can move in without breaking the underlying rules. The path is not selected from freedom. It is carved out by restriction. Even randomness, which we often treat as the opposite of constraint, is not truly free in physics. When a particle decays, or when quantum outcomes appear uncertain, the uncertainty is not unlimited. It is confined within strict probability distributions. Those distributions are not chosen on the fly. They are fixed by deeper mathematical structures that never change. So even what we call random events are not outside the framework of constraint. They are expressions of it. This becomes even clearer when you look at conservation laws. Energy cannot be created or destroyed. Momentum cannot simply disappear. Angular momentum remains constant unless exchanged through interaction. These are not suggestions. They are not tendencies. They are absolute boundaries. They define what transformations are allowed and what transformations are impossible. And here is the key shift. The universe does not enforce these rules like a system checking compliance. There is no mechanism for watching events and correcting them. Instead, the rules define the space of possibility so tightly that violations never arise in the first place. It is not that forbidden outcomes are prevented. It is that they are never part of reality's option set at all. This is where the idea of decision completely breaks down. Decision implies multiple valid paths and a selection process between them. But in physical systems, what looks like multiple paths is actually a narrow structure of allowed evolution. The system does not choose between valid futures. It evolves through the only futures that are mathematically consistent. Even in complex systems like weather patterns or galaxy formation, where behavior appears chaotic, the underlying structure is still constraint-driven. There are countless interacting variables, but none of them operate outside the boundaries set by fundamental laws. Turbulence does not break rules. It unfolds inside them. Complexity does not mean freedom from structure. It means structure operating at a scale too intricate to predict easily. At quantum scales, this becomes even more striking. Particles do not carry internal debates about where to go or what state to adopt. Their behavior is constrained by wave functions, operators, and probability amplitudes that define what outcomes are possible. Measurement does not force a decision from infinite possibilities. It reveals one outcome from a pre-filtered set of allowed results. The range of possibilities was never infinite to begin with, and when you zoom out to the largest scales, galaxies, clusters, cosmic filaments, the same principle repeats. The universe does not randomly assemble matter into structureless chaos. It organizes matter into configurations that satisfy gravitational constraints over enormous timescales. Filaments form because they are stable outcomes under gravity. Voids exist because matter redistributes itself within the limits of expansion and attraction. Nothing escapes the framework. This is where a subtle misunderstanding often appears. Because systems can be complex, we assume they must be less constrained. But complexity does not weaken constraints. It multiplies the ways constraints express themselves. A single rule applied across many interacting parts produces outcomes that look unpredictable, but the rule itself never loosens. In fact, the more complex the system, the more deeply the constraints are embedded in its behavior. Think of it like a landscape. The universe does not push objects towards certain outcomes. It defines the shape of the terrain. Valleys, slopes, and boundaries determine how anything moves. You can imagine countless paths across the landscape, but you cannot step outside the terrain itself. You do not decide where gravity pulls you. You simply respond to the shape of space already given. And here is where the idea becomes even more precise. Constraints are not external to the universe. They are not rules written above reality. They are encoded within the structure of reality itself, the geometry of space-time, the symmetries of physical laws, the conservation principles. These are not instructions imposed from outside. They are the internal grammar of existence. So when we say the universe does not decide, we are not removing intelligence and replacing it with emptiness. We are correcting a misunderstanding about what kind of system reality actually is. It is not a chooser of outcomes. It is a generator of allowed configurations. Nothing in physics requires selection from unlimited possibility. Instead, everything is shaped by a continuously active filtering process, defined by law-like structure. What survives that filtering is what we call reality. What fails, it never exists at all. And once you see this clearly, even familiar ideas begin to shift. Cause and effect no longer look like a chain of decisions. They look like a continuous unfolding inside a fixed structure. Time does not choose what happens next. It simply moves the system through states that already satisfy every constraint at every step. The result is a universe that feels dynamic, but is fundamentally non-arbitrary. A universe where nothing is negotiated, nothing is chosen, and nothing is improvised. Every outcome is the direct consequence of structure that was already in place. So the deepest correction is this: the universe is not making decisions about reality. It is defining what reality is allowed to be, and everything we observe is what remains after impossibility has already been removed. The quantum level shock. At the smallest scale we can meaningfully describe, the universe stops behaving like anything we intuitively recognize. The idea of smooth motion, clear paths, or continuous change begins to break down. Instead, reality becomes granular, statistical, and strangely indirect. This is the quantum level, and it does not behave like a smaller version of classical physics. It behaves like an entirely different rulebook. What makes this level shocking is not just that things are uncertain. It is that uncertainty itself is structured. Particles do not wander freely through space in the way dust moves in air. They exist in states that are defined by probability distributions, mathematical objects that describe where something could be found if measured, not where it is in a classical sense before measurement. This creates a fundamental shift in how motion and position must be understood. In everyday experience, an object has a location even if we are not looking at it. At the quantum level, that assumption fails. A particle is not described by a single fixed point in space. It is described by a range of possible outcomes, all existing in a mathematically consistent relationship, until interaction forces a specific result to appear. But even that appearance of a result is not a decision made by the universe. It is the outcome of constraints built into the structure of quantum mechanics itself. The wave function evolves according to precise equations. Nothing about it is arbitrary or emotionally random. It does not explore possibilities freely. It follows a strict mathematical evolution that continuously reshapes probabilities according to fixed rules. And yet, when we perform a measurement, we do not see probabilities. We see a single outcome. This is where the shock begins. A system that behaves in smooth, deterministic mathematics suddenly produces discrete events, not because the underlying rules are inconsistent, but because the act of observation forces the system into one of its allowed configurations. It is important to understand what this does not mean. It does not mean that consciousness creates reality. It does not mean that observation is a mystical force. What it means is far more precise. Interaction with a measuring system reduces a set of allowed possibilities into a single realized outcome that still obeys all constraints of the theory. In other words, nothing breaks the rules. Even collapse, the moment when a quantum system produces a definite result, is not outside the law. It is part of the law. Mathematics already includes the structure that limits what can be observed. The shock is not that reality becomes unpredictable. The shock is that predictability exists only at the level of probabilities, not outcomes. This is where quantum physics begins to feel like a reversal of everyday logic. In classical thinking, causes produce effects in a direct chain. In quantum systems, causes produce distributions of effects. You do not predict a single event. You predict the shape of all possible events, and reality selects one point inside that shape without violating the structure that defined it. Even more surprising is how deeply symmetry still operates here. The same idea that governed galaxies and conservation laws also governs quantum behavior. The equations remain invariant under transpositions. The structure does not change if you shift perspective, rotate reference frames, or evolve forward in time. What changes is only the expression of outcomes inside that structure. So even at this level, nothing is truly free. The system is not improvising. It is unfolding inside a tightly defined mathematical space where every possibility has already been filtered by constraints before any measurement occurs. This leads to a deeper realization. Quantum uncertainty is not absence of structure. It is a structure expressed in a different form. Instead of fixed trajectories, you get probability waves. Instead of definite positions, you get distributions. Instead of deterministic outcomes, you get constrained possibilities that only appear random because you are observing them from outside the full mathematical description. And this is where the connection to everything else becomes unavoidable. The same universe that forms galaxies through gravity and organizes matter through conservation laws is also the universe that operates through quantum constraints at the smallest scale. There is no separation between these layers, only different expressions of the same underlying structure. The shock, then, is not that the quantum world is strange. The shock is that it is consistent with everything else. The same logic that governs cosmic rotation also governs subatomic uncertainty. The same constraints that prevent energy from being destroyed also shape probability itself. When you reach this level of description, the idea of randomness begins to dissolve. What remains is not chaos, but a deeply structured space of possibilities that the universe moves through with absolute precision, even when the outcome looks uncertain from the outside. And that is the core realization of the quantum level. Reality does not become less structured when you go smaller. It becomes structured in a way that no longer looks familiar. The hidden geometry of fields. When we talk about fields in physics, we are referring to something most people never directly visualize, even though it fills every part of reality. A field is not a substance like air or water. It is not an object you can point to. It is a continuous structure assigned to every point in space, describing how particles and forces behave at that location. The electromagnetic field, the gravitational field, the Higgs field. These are not things inside space. They are what define how space behaves. At first glance, fields seem like a mathematical convenience, a way to describe forces without needing invisible particles constantly pushing and pulling. But as physics developed, fields stopped being optional descriptions and became the central language of reality. Everything we call a particle is now understood as an excitation of an underlying field. In this view, electrons are not tiny balls orbiting a nucleus. They are localized vibrations in the electron field. Photons are not little bullets of light. They are ripples in the electromagnetic field. This already changes the way reality must be imagined. But the deeper shift comes when we realize that these fields are not independent. They are not separate layers stacked on top of each other. They are interconnected structures obeying shared symmetries and constraints. And those constraints shape what kinds of behavior are even possible. What appears as physical motion is really the evolution of field configurations. When something moves, nothing is actually traveling through empty space in the classical sense. Instead, the field's excitation shifts from one region to another, like a pattern being continuously redrawn, rather than a single object moving across a blank background. And this is where geometry enters in a surprising way. We normally think geometry is the stage on which fields exist. Space defines distances, angles, and directions, and fields operate inside that framework. But modern physics suggests something more subtle. The structure of fields and the geometry of space are deeply entangled. In some approaches, they are not separate at all. Geometry may emerge from field interactions, rather than fields existing inside geometry. This means that what you perceive as distance is not fundamental. It is derived from relationships between field values. What you perceive as shape is not pre-given. It is reconstructed from how fields correlate across space. Even the smooth continuity of space may be an approximation of deeper underlying relationships. The universe stops looking like a container filled with objects and starts looking like a network of interacting quantities. Every point in space is defined not by its position in an empty grid, but by how it relates to everything else through field values. If those relationships change, the notion of geometry itself changes. This is why the phrase hidden geometry is not poetic exaggeration. It is literal. The geometry is not fully visible at the level of everyday experience. It is encoded in equations describing how fields evolve and interact. And those equations do not simply sit on top of space, they generate the behavior of space itself. Now connect this back to motion and rotation. Angular momentum, which we usually associate with spinning objects, is also deeply tied to field structure. When something rotates, what is actually conserved is not just the motion of a rigid body, but a symmetry embedded in the field equations. Rotation symmetry in fields ensures that angular momentum remains constant across interactions. That is why spin shows up everywhere, from electrons to galaxies. It is not an added feature. It is a consequence of how fields are built. Even more interestingly, some modern theories suggest that spin and geometry may not just be connected, but interchangeable at a fundamental level. In certain quantum gravity approaches, geometry itself can be described using spin networks, structures where the fundamental elements are not distances or coordinates, but quantum spin relationships. In this picture, space is not something fields sit inside. Space is something that emerges from the structure of field interactions that carry spin information, so the distinction between field and space begins to blur. What we call space may simply be the macroscopic result of countless underlying field relationships. The smooth geometry we experience could be a large-scale approximation of discrete, quantized interactions happening at a level far beyond direct observation. This leads to a striking conclusion. The universe does not need a pre-existing geometric stage for fields to act on. Instead, geometry itself may be a bookkeeping result of field behavior. What we perceive as distance, curvature, and structure may be secondary effects of something more fundamental. Relational patterns in fields governed by symmetry and constraint, and once again, symmetry appears at the center. Fields are not arbitrary. Their forms are restricted by symmetry principles that determine how they can change, how they interact, and what remains conserved. These constraints are what give rise to the stable patterns we recognize as particles, forces, and structures. So the hidden geometry of fields is not just about what space looks like underneath. It is about the idea that space, at its core, might not be a thing at all. It might be the visible trace of deeper mathematical relationships. Relationships that are continuously active, continuously constrained, and continuously shaping what reality can become. And in that sense, the geometry is not hidden because it is far away. It is hidden because it is doing the work that makes far away possible in the first place. Space is not empty. When we picture space, we usually imagine emptiness, a kind of blank stage where things happen. Objects move through it, light travels across it, and forces act inside it. It feels like nothingness, a passive background waiting to be filled. But modern physics removes that picture completely. Space is not empty. It is active, structured, and constantly involved in everything that exists. The first challenge to the idea of empty space comes from fields. Even when no particles are present, fields still exist everywhere. The electromagnetic field, gravitational field, and other fundamental fields are never switched off. They fill all regions of space continuously. So even in what we call a vacuum, there is still structure. There is still something there, just not something visible in the traditional sense, but it goes deeper than that. In quantum physics, the vacuum is not truly silent. It is restless. Even in the lowest possible energy state, fluctuations appear and disappear constantly. Particle-antiparticle pairs can briefly emerge and vanish. Energy levels are never completely static. This is not because something external is disturbing space. It is because the vacuum itself is defined by quantum rules that never allow complete stillness. So what we call empty space is actually a state full of activity that cannot be removed. It is not a void. It is a lowest energy configuration of something still fundamentally alive with structure now. Consider what this means for the idea of distance and separation. If space is not empty, then distance is not just a gap between objects. It is a region filled with interacting fields. Two objects are not separated by nothing. They are separated by a medium that has properties, rules, and behavior. Even if nothing material exists between them, the fields that define physical law still do. This changes the meaning of interaction itself. When two particles influence each other, they are not reaching across emptiness. They are interacting through the structure of space itself. Forces like gravity and electromagnetism are not transmitted through voids. They are expressions of the structure that fills those regions. Space, then, is not passive. It carries energy, it carries fluctuations, and it carries the rules that determine how everything evolves. It is not a background stage. It is part of the performance. At a deeper level, some theories suggest that space might even be emergent. That means space is not fundamental at all, but arises from more basic relationships between underlying entities. In this view, what we perceive as distance is actually a consequence of how strongly different parts of a system are connected. If the connections change, the geometry of space changes with them. This idea removes the final layer of emptiness completely. If space is built from relationships, then there is no point where nothing exists. There are only degrees of connection. The universe becomes a network of interactions rather than objects inside a container. Even gravity supports this shift in thinking. In general relativity, gravity is not a force moving through empty space. It is the curvature of space-time itself. Mass and energy reshape the structure of space, and that structure tells objects how to move. So what we call gravitational attraction is actually geometry responding dynamically to presence. This means space is not separate from matter. It responds to matter. It changes with matter, and in some interpretations, it may even arise from the same underlying principles that produce matter itself. The separation between things and space begins to dissolve. The idea of emptiness becomes misleading. There is no true void in which nothing exists and nothing happens. Even the lowest possible state of reality contains structure, activity, and constraints. Space is always doing something, even when it appears still. And this is the key realization. If space is never empty, then nothing in the universe is ever isolated. Every object, every particle, every field exists within a continuous environment of structure. There is no absolute separation, only varying degrees of interaction. So when we say space is not empty, we are not just correcting a scientific detail. We are correcting a fundamental intuition about reality. We are removing the idea that the universe is built on nothingness and replacing it with something far more profound. Space is not the absence of things. It is the structure that makes things possible in the first place. Time is not free flow. Time feels like the most obvious thing in the universe. It seems simple. The past is behind us, the future is ahead, and everything moves forward in a straight line. We wake up, we grow older, we remember yesterday, and expect tomorrow. Because of this constant experience, it feels like time is something flowing independently, like a river carrying everything forward without exception. But physics does not describe time as a flowing substance. It describes time as a dimension, similar in structure to space, where events are arranged rather than carried. In the equations of relativity, time is not something that moves. Instead, it is something that is already there, with all moments existing as part of a single structured space-time geometry. This means the feeling of flow is not a property of time itself. It is a property of how information is processed inside the brain. We experience time moving because memory stores earlier states, while awareness exists in the present state. The contrast between stored information and current perception creates the sensation of motion. But even more important is this: time is not independent from the rules of the universe. It is deeply tied to energy, gravity, and motion. In strong gravitational fields, time slows down. Near massive objects like black holes, time can stretch so dramatically that minutes for one observer become years for another. This is not theoretical imagination. It has been measured using precise atomic clocks. So time is not a universal clock ticking equally everywhere. It is flexible, shaped by conditions in the universe itself. This destroys the idea of time as a simple background stage. Instead, time behaves more like a structured layer that bends, stretches, and adapts depending on where and how it is observed. When we combine this with quantum physics, things become even more unsettling. At microscopic scales, equations do not require a single direction of time. Many physical processes work the same, whether time runs forward or backward. The arrow of time we experience emerges not from fundamental rules, but from statistical behavior, from the tendency of systems to move toward higher disorder. This leads to a deeper question. If the fundamental laws do not strongly enforce a direction, then why does our universe feel so strongly one-directional? Why does memory only form backward? Why does cause always appear before effect? The answer lies in entropy, the tendency for energy to spread out, and systems to become more mixed over time. Once a system becomes more disordered, returning to its exact previous state becomes so unlikely that it effectively never happens in practice. This creates a one-way experience, even if the underlying equations do not strictly forbid reversal. So what we call time flowing is actually a macroscopic effect created by statistical behavior, memory formation, and energy distribution. It is not something imposed from outside the universe. It is something generated inside it. And this changes everything, because if time is not a flowing entity, but a structured dimension shaped by physical law, then the universe is not moving through time. It is existing across time. Every moment is part of a larger structure, and our experience of motion is only a narrow slice of a much deeper geometric reality. Time is not free flow at all. It is a constrained structure, just like everything else in the universe. Why everything moves in patterns. At first glance, the universe looks chaotic. Clouds drift in unpredictable shapes. Stars form in distant regions without warning. And particles in quantum physics appear to behave randomly when observed individually. From a human perspective, it feels like reality is full of irregular motion with no consistent direction. But once we step back and zoom out, a completely different picture appears. Instead of randomness, we begin to see repetition. Instead of disorder, we see structure. Motion in the universe is not scattered, it is patterned. Planets do not drift randomly through space. They follow stable orbits. Even when disturbed, they tend to settle back into predictable paths shaped by gravity. Galaxies are not arranged without structure either. They form spiral arms, rotating disks, and large-scale filaments that stretch across the universe in repeating cosmic patterns. Even gas clouds in space collapse into familiar shapes: spheres, disks, and spirals. This repetition is not accidental. It comes from constraints imposed by physical laws. Gravity pulls matter inward, but angular momentum resists collapse into a simple point. Instead of falling straight in, matter spreads into rotating structures. This combination, inward pull and rotational resistance, creates repeating geometries at every scale. The same logic appears again and again in different forms. Atoms form because electrons occupy stable energy levels rather than collapsing into the nucleus. Stars form because gas clouds reach equilibrium between pressure and gravity. Galaxies form because dark matter and baryonic matter settle into stable gravitational configurations. Each system is different in detail, but the underlying pattern is the same. Balance between opposing forces creates structure. Even when we look at microscopic physics, patterns still dominate. Quantum fields do not behave like random particles, appearing and disappearing without rule. Instead, they follow precise mathematical relationships that determine how probabilities evolve. What appears random at the level of individual events becomes predictable when observed statistically across large numbers of interactions. This is one of the most important shifts in scientific thinking. Randomness at small scales does not prevent structure at large scales. In fact, large-scale order often emerges from small-scale uncertainty. Systems that appear chaotic locally can produce stable patterns globally, as long as the underlying rules remain consistent. Another reason patterns appear everywhere is that the universe tends to evolve toward equilibrium states. Systems do not remain in extreme or unstable configurations for long periods. Energy spreads out, differences equalize, and interactions smooth out irregularities over time. This tendency does not erase structure, it shapes it. Instead of producing uniform emptiness, it produces stable forms that can persist. What is most striking is that these patterns are not imposed externally. There is no visible designer adjusting the structure of galaxies or the motion of particles. The patterns emerge naturally from the rules themselves. Gravity, electromagnetism, quantum mechanics. Each fork contributes constraints, and those constraints repeatedly produce similar outcomes across completely different environments. This is why we can recognize familiar shapes across the universe. A spiral galaxy resembles a hurricane. An accretion disk around a black hole resembles a forming solar system. Even atomic orbitals show wave-like symmetry that echoes large-scale structures. The scale changes, but the pattern logic remains consistent. So when we say, everything moves in patterns, we are not describing an aesthetic observation. We are describing a deep structural fact about reality. Motion is not freeform. It is guided by constraints, and those constraints are stable enough to repeat across time, space, and scale. And once this is understood, the idea of randomness begins to weaken. What we call randomness may often be the surface appearance of deeper, repeating rules we have not fully recognized yet. The universe favors stability. If you observe the universe closely enough, a strange tendency begins to appear. Unstable things do not last. Systems that are chaotic, imbalanced, or highly energetic tend to change rapidly until they reach something more stable. Not necessarily perfect, not necessarily simple, but stable enough to persist. This is not a philosophical idea. It is a repeated outcome across physics, from the smallest particles to the largest cosmic structures. At the atomic level, electrons do not spiral into the nucleus, even though classical physics would suggest they should. Instead, they settle into specific energy levels where the system becomes stable. Any attempt to force them into a different state requires energy input. Once that energy is removed, the system returns to equilibrium. Stability is not optional. It is enforced by the structure of quantum rules. At the planetary scale, orbits are not random paths. Planets do not crash into their stars or fly away into space without reason. Over time, gravitational interactions tend to eliminate extreme trajectories. What remains are stable orbits, balanced paths, where motion and gravity continuously counteract each other. These are not the most energetic configurations, but the most sustainable ones. Even in violent cosmic events, such as star formation or supernova explosions, the final outcome is not chaos. A collapsing star does not remain in a disordered state. It becomes a neutron star, a black hole, or disperses into structured gas clouds that later form new stars. Out of destruction comes reorganization. Out of instability comes a new equilibrium. This tendency becomes even more visible on galactic scales. Galaxies do not form as random collections of stars moving unpredictably. They evolve toward configurations where gravitational forces and angular momentum balance each other. Spiral arms, rotating disks, and halo structures are not accidental shapes. They are stable arrangements that persist over billions of years. The same principle appears in thermodynamics. Systems naturally move toward states where energy is more evenly distributed. Heat spreads, pressure equalizes, and gradients smooth out. This process does not eliminate structure entirely. It removes unstable differences and leaves behind configurations that can endure. What is important here is not that the universe wants stability in a conscious sense. There is no intention behind it. Instead, stability emerges because unstable configurations are statistically unlikely to persist. They either decay, transform, or evolve into something that can last longer under the same rules. This creates a universe where long-lived structures dominate what we observe. Short-lived chaos exists, but it rarely defines the final outcome. Stars, planets, galaxies, and atoms are all examples of systems that have found ways to persist under constant physical pressure. Even time-dependent processes reflect this pattern. When systems evolve, they do not move randomly from one state to another. They tend to pass through transitions that reduce instability step by step. Each stage is constrained by energy, momentum, and interaction rules, gradually guiding the system toward equilibrium. This is why the universe is filled with recognizable structures instead of constant turbulence. Stability acts like a filter. It removes everything that cannot sustain itself long enough to become part of the large-scale picture. So when we say, the universe favors stability, we are not implying choice or direction. We are describing a statistical outcome of physical laws. Out of all possible configurations, only those that can survive interaction, dissipation, and time remain visible. And what we observe today, from atoms to galaxies, is the record of everything that managed to stay stable long enough to still exist. Life as a consequence of order life does not appear in the universe as something separate from physics. It is not an exception to the rules, and it does not operate outside them. Instead, life emerges from the same physical constraints that shape everything else: gravity, energy flow, chemical bonding, and time evolution. At first glance, life looks like the opposite of order. It grows, adapts, changes direction, and reacts to its environment in ways that feel unpredictable. But this apparent complexity is built on a foundation of extremely strict structure. Every biological process depends on stable physical laws that never change, from the behavior of electrons in atoms to the way molecules interact in chemical reactions. Without those stable laws, life would not even be possible. If atoms did not maintain consistent energy levels, chemistry would collapse. If molecules did not form reliable bonds, no stable structures could exist. If energy did not flow in predictable ways, there would be no sustained processes to support metabolism, growth, or reproduction. Life exists because the universe allows energy to flow through structured pathways rather than random dispersion. In thermodynamic terms, living systems are not isolated pockets of order resisting chaos. They are open systems that maintain internal organization by continuously exchanging energy with their surroundings. They take in energy, use it to sustain structure, and release waste energy back into the environment. This creates a paradox that is often misunderstood. Life increases local order, but it does so by increasing overall entropy in the universe. A living organism maintains internal complexity only because it is constantly participating in larger energy flows that move toward equilibrium. In other words, life does not violate the tendency toward disorder, it rides on top of it. The most important feature of life is not its complexity, but its ability to preserve information over time. DNA, for example, is a stable molecular structure that stores instructions across generations. This stability is not accidental. It comes from chemical properties that make certain molecular configurations more durable than others. Once again, stability is selected by physics. Even evolution itself is not random in the way it is often described. Mutations may occur without direction, but selection is highly constrained. Only variations that can survive environmental conditions persist. This creates a process where randomness is filtered through structure, producing increasingly adapted forms over time. Biological systems reflect the same patterns seen in non-living systems. Energy gradients drive motion. Feedback loops create stability. Networks form because they are efficient ways to distribute resources. Neural activity in the brain follows electrical and chemical rules that are fundamentally physical in nature. What makes life feel distinct is not that it breaks from physics, but that it uses physics in highly organized ways. It builds complexity by stacking layers of stable interactions, molecules forming cells, cells forming tissues, tissues forming organisms. Each level depends on the stability of the one below it. Life is not an anomaly in the universe. It is a natural consequence of a system where order emerges from energy flow under strict constraints. Where conditions allow long-term stability, structure accumulates. Where structure accumulates, information persists. Where information persists, self-organizing systems become possible. So life is not something added to the universe. It is what the universe becomes when order is sustained long enough to begin reflecting itself. The final realization after all the layers, randomness and structure, time and motion, stability and life. A single pattern keeps reappearing. The universe does not behave like a collection of independent events. It behaves like a tightly constrained system where everything is connected through rules that never change. At every scale we examine, the same structure appears in different forms. Particles follow conservation laws. Atoms form stable configurations. Stars and galaxies organize through gravity and angular momentum. Even life, which feels most unpredictable, emerges only where stable physical conditions allow it. Nothing exists outside these constraints. Everything is shaped by them. This leads to a shift in perspective. What we call reality is not a set of things floating freely in space and time. It is a network of relationships that cannot be broken without destroying the structure itself. Change is allowed, but only within limits. Motion is possible, but only along defined paths. Complexity emerges, but only when stability supports it. When we trace these constraints deeply enough, we begin to see that the universe is not built from isolated objects. It is built from rules that act continuously across everything. These rules do not depend on location or scale. They apply equally to atoms, planets, galaxies, and everything in between. And because these rules are consistent, the universe develops recognizable patterns. It does not need guidance or correction. It evolves naturally toward configurations that satisfy its own constraints. That is why structure appears everywhere, not because it is imposed, but because it is unavoidable. Randomness becomes less absolute. What appears random at one level may simply be the result of hidden constraints at another level. Complexity does not mean lack of order. It often means order operating across many layers at once, where simple rules interact to produce complex outcomes. The most important realization is this: the universe is not something we move through as passive observers. We are part of the same structured system. Every thought, every action, every physical process inside us follows the same rules that govern everything else. There is no separation between observers and system at the fundamental level. There is only one continuous structure unfolding through different scales, from quantum fluctuations to cosmic evolution. So the final realization is not about discovering a hidden object or a secret force. It is about recognizing that what we call reality is already structured in a way that is consistent from beginning to end. And once this is seen clearly, the idea of chaos as something independent disappears. What remains is a single system, evolving, constrained, and coherent, where everything that happens is part of the same underlying order. So the question is not whether the universe is random. The real question is, how much of what we call randomness is just hidden order we haven't understood yet? Because every layer we explore, matter, energy, space, time, refuses to behave like chaos. It behaves like something designed not by intention, but by mathematical inevitability. And maybe that is the deepest truth of all. The universe is not uncertain. We are simply incomplete in our understanding of its rules. And the moment we fully understand them, reality will stop looking like a mystery and start looking like a structure.